back to my YouTube channel, PhDing. In this part 2 of a 3-part series of running a regression diagnostics, I'm going to show you what are the commands you need to run in Stata. But before you jump to this part, make sure you have watched part 1 to make so the things make sense to you while you watch the video. Part 1 explains what you do once you get a data and you are asked to run a regression analysis, while this part will show you what are the steps before running a specification analysis so that you can eventually finalize your final regression model. So in the prior series, part 1 video, I have explained my global Y list and X list, and also in this part, I'll go ahead and just run a correlate command. Correlate would do a correlation analysis of the variables you want to run the regression for. So you can see, so diagonally, it's completely 1 score because the variables correlate with themselves. But if you read is for-profit status has about 0.09 correlation with the average daily activity score of the nursing homes, so on and so forth. Two main things to look on this results table of correlation is the positive and negative signs of the score, as well as if any scores are near to 0.5, which means strong correlation, but if there is close to a score which is somewhere around 0.9 or above 0.8, then chances are the variables might show you issues of multicollinearity or redundancy while you run a regression. Different texts have different rule of thumb in order to consider for multicollinearity, but the agenda for running a correlation analysis is to see the direction of the correlation between the variables of your regression, as well as the strength of correlation, and if any presence of multicollinearity, and if two variables mean the same, you can automatically exclude one of the variables. The polychoric correlation is a user-written command. So for this command, you'll have to install the application in your Stata, but this does the same job. The correlate command has a mixture of continuous and categorical variables, so I can't separate them. If you were to separate it and write specific names of the variables, you can just put an I integer I in front of the variable names for those which are categorical variables and run the correlations analysis, and it will give you the same results. While polychoric correlation takes care of if your regression analysis is going to have a mixture of categorical variables and continuous variables, which my data already has and my variable list has. So even though it takes a while to run, you can run a polychoric correlation and compare your results. So we can see if you, well, they're almost close to same, but sometimes, like say for an instance, total beds and the proportion of Black patients have a correlation of, let's see, 0.28, 0.284. It's almost close to similar, but some values are different, like for profit, so on and so forth. But the way you would read this table and interpret is similar to how you would do when you run a correlate analysis, correlate command. Now you'll go ahead and run your basic OLS, your regression model. I know because I ran this command before that my data has a presence of heteroscedasticity, and I'll show you how to run the test for it in part 3 for specification analysis. But for now, because there's a presence of heteroscedasticity, I'm going to use the VCE robust command to kind of make the standard errors of the coefficient small. So key thing to remember is if there is a presence of heteroscedasticity in your data, this command VCE robust takes care of your standard errors. So it makes it smaller, but nothing else. It doesn't have any effect on your beta coefficients significance. So running a regression, the way you interpret this is your R-squared. So basically about 14% of the variance in your outcome variable, which is your Y, is explained by the model, by these variables in the data. And these are your beta coefficients. These are the standard errors. These are your significance values, and they seem, all the variables pretty much seem significant. These are the confidence intervals, 95% confidence intervals. But let's just not hog on the basic OLS, because eventually after you run a specification analysis, you'll realize a much better proportion of the variance in your outcome variable can be explained if you use a specific model which suits the data and your research question after taking care of violations if they are present in your regression analysis. For now, when you go, so the next step is this is optional, like if you want to run a wald test for equality of coefficients, which basically means that if any of your X list variables have a different score for the outcome variable. So let's just say I'm running a wald test for coefficient. I just want to see if my for-profit status has a different values for the average daily score activity. So is there a difference in patients who are in a nursing home that has a status of for-profit differ in their average daily activity scores? So by running a test command for-profit, I can see my significance, my p-value is less than 0.05, which means there is a significant difference in scores of outcome variable for the status of nursing home. And you can run likewise for the rest of your variables. Here I run my entire X list to see, to do the wald test of significance. I'm not a huge fan of significance because the key thing you have to pay attention is in the confidence intervals. Is it a broad confidence interval, or is it a narrow confidence or accurate confidence interval? Because many factors go in the p-values. If there's a small sample size, if other variables are omitted in your regression, so it basically means there is a presence of selection bias, and hence the reason your standard errors are affected, and finally your p-values. So here we see the tests for all my variables come out as the p-value is significant, which means all my covariates and independent variables have the different scores for the average daily activity score, which is my outcome variable. The final step in this section is to run so you add each variable from your right hand side, your independent variable, then keep on adding the covariates. You finalize a short list to include in your regression analysis. The reason we do this section is to see key things you have to see is, does your independent variable's coefficient change while you add your covariates? And then finally, the R-square, which would be at the bottom of the table, I'll show you in a while. if that increases, which means does the variance explanation in your outcome variable improve while you keep on adding the covariates. And finally, you would understand if there is a presence of omitted variable bias, which I'm going to show you in the part 3 series. But for now, let's just run. So estimates command would store each regression in your working directory, and then at the end, when you call all the regressions, it would show you all the regressions you have run prior in a single table for you to make the job easy to understand. So also make sure once you run the first regression, I'm using VC robust because there's a presence of heteroscedasticity in my data, as I explained before. But every time you run the regression, you store with a different regression name. So the first regression, I named it as an object of reg 1, reg 2, and so on and so forth. So when you call them, it makes sense at the end. I'm going to go ahead and run all the variables and then run the command. Now you can see that, as I explained before, how to interpret this is when you just compare with your independent variable for your outcome variable, you can see the model only, the regression model only explains 0.009, which is like almost negligible. But when you go to reg 2 and you add on your covariate, which is average age, the coefficient does change. The independent variable, which is your status of nursing home, changes from 0.62 to 0.78, which is 0.8, almost close. Which means that there is a presence of omitted variable bias because your independent variable keeps on changing. Now, if you see the R-square, it has improved, which is basically 3%. The variance in your outcome variable is explained by the regression model 2 of about like 3%. So on and so forth. So when you see there is a significant change in regression 5 and regression 6 when you add it, so in your regression 5, you add PM Medicaid and then total number of beds, which indicates something that if they were absent, that is why there is a higher for-profit status beta coefficient values. And when you keep on adding appropriate relevant variables, your independent variable coefficient changes because now the variance in your outcome variable is explained by the variables you add later on. You also have to pay attention, as I explained, is to the R-square. You see the regression 6 explains about 14% of variance in your outcome variable. So regression 6 seems to be an appropriate OLS, but in the next part 3, I'll explain you what to look for and maybe the violations of the regression model. A regression analysis can also give you skewed results of both beta coefficients. But for now, thanks for watching this video, and make sure you watch part